Close your eyes for a moment and imagine a cloud. Not the soft, fluffy kind drifting over a summer afternoon, but something so enormous it would swallow our entire solar system like a crumb in an ocean. That's a nebula, and it's not just sitting there doing nothing. The word nebula comes from the Latin word for cloud, and early astronomers used it to describe any fuzzy, glowing smudge they spotted in the night sky. For centuries, nobody truly knew what these ghostly patches of light were. Some thought they were distant galaxies. Others believed they were planetary systems being born. They were, in a sense, both right. A nebula is a vast region of interstellar gas, dust, and plasma scattered across space in breathtaking proportions. They are, in the truest sense, the fabric of the universe caught mid-breath. These are not empty, passive structures. They are alive with chemistry, with motion, with magnetic forces tugging and threading through their depths like invisible fingers. Nebulae are made mostly of hydrogen and helium, the two simplest, most abundant elements in the universe, with traces of heavier elements sprinkled throughout. These heavier materials, like carbon, oxygen, and iron, were forged in the hearts of older stars that exploded and scattered their contents across the cosmos long before our sun was born. What makes nebulae so extraordinary is that they are both a beginning and an ending. They are the graveyards of ancient stars and the nurseries of new ones. Every atom in your body was once part of a nebula. Every breath you take carries atoms that may have drifted through the dark between galaxies for billions of years. Nebulae are not just beautiful, they are profoundly, intimately connected to everything that exists.
Here's something that should stop you cold. The universe is mostly made of nothing, or at least almost nothing. The vast stretches between stars are not empty. They're filled with incredibly thin gas and dust, spread so thinly across space that a cubic meter of it would contain only a handful of atoms. On Earth, that would be a vacuum. In space, it's the raw material of everything. The interstellar medium, the technical name for this cosmic filling, is a staggering recipe. Roughly 70% hydrogen, 28% helium, and just about 1.5% heavier elements by mass. That last 1.5% sounds insignificant, but it's where things get interesting. Those heavier elements, carbon, nitrogen, oxygen, silicon, iron, are the building blocks of planets, of chemistry, of life. They were born in stellar furnaces and scattered across the cosmos by explosions so violent they briefly outshine entire galaxies. The dust in the interstellar medium is not like household dust. These are microscopic grains, silicates, carbon compounds, ices that absorb and scatter starlight in beautiful, eerie ways. They turn distant stars red, they create glowing halos, they build dark curtains that hide entire star-forming regions from our view. And yet, for all their drama, these grains are smaller than a human hair. This raw material has been cycling through the universe for over 13 billion years. It forms stars, which fuse lighter elements into heavier ones, then explode and return enriched material back to space. Each new generation of stars is slightly more chemically complex than the last. We are, in a very literal sense, made of the universe's most processed ingredients, stardust that has been through the cosmic kitchen more times than we can count. The raw material of nebulae is ancient, it is patient, and it has been waiting in the cold dark between stars for gravity to come calling. If you thought a nebula was just one thing, the universe has some spectacular news for you. Nebulae come in an astonishing variety of shapes, sizes, colors, and behaviors, and each type tells a completely different story about what's happening inside it. Calling all nebulae the same thing is like calling all weather, weather. Technically accurate, wildly insufficient. Emission nebulae are perhaps the most iconic. These glowing clouds of ionized gas, superheated by nearby young stars, blaze in shades of red, pink, and violet. They are the ultimate cosmic light show, and they are actively making stars right now. The Orion Nebula, the Eagle Nebula, the Lagoon Nebula, these are emission nebulae, and they are some of the most photographed objects in the universe. Reflection nebulae don't glow on their own. Instead, they scatter and reflect the light of nearby stars, often appearing in cool, haunting blues. They're the cosmic equivalent of moonlight, beautiful but borrowed. Dark nebulae are shadowy giants, dense clouds of dust, so thick they block the light of everything behind them, carving dark silhouettes against brighter backdrops. The Horsehead Nebula is one of the most famous, a dark pillar rising against a glowing emission nebula, like a chess piece made of shadow. Then there are planetary nebulae, having nothing to do with planets. The name is a historical accident. Early astronomers thought their round, glowing shapes resembled planets through small telescopes. They are actually the ejected outer shells of dying sun-like stars, puffed outward and luminous symmetrical rings and shells. Then there are supernova remnants, the wild, tangled wreckage of massive superstars expanding outward in twisted filaments of superheated gas. The Crab Nebula, born from a supernova witnessed by Chinese astronomers in 1054 AD, is still expanding today. Each type of nebula is a chapter in a story that stretches across billions of years. Imagine the universe as an ocean, and the stars as islands scattered across it. Most people spend all their time looking at the islands, but what fills the unimaginable space between those shining points of light? That in-between space has a name, the interstellar medium, and it's far stranger and more alive than most people realize. The interstellar medium, or ISM, is not empty. It is a diffuse, ever-shifting mixture of gas, dust, cosmic rays, and magnetic fields woven throughout every galaxy. It exists in multiple phases simultaneously, ranging from extremely hot and thin plasma millions of degrees hot to cold, dense molecular gas just a few degrees above absolute zero. These phases coexist, crash into each other, compress, expand, and constantly exchange energy in ways that astrophysicists are still working to fully understand. The chemical richness of the ISM is staggering. Scientists have detected over 200 different molecules floating in interstellar space, including water, alcohol, ammonia, formaldehyde, and even complex organic compounds like glycolaldehyde, a sugar-related molecule. The universe was doing organic chemistry long before life ever appeared on Earth. The density, though, is almost incomprehensibly low. In the densest molecular clouds, the regions most likely to form stars, there might be 10,000 molecules per cubic centimeter. That sounds like a lot, until you realize that the air you're breathing right now contains about 27 billion molecules per cubic centimeter. The densest nebulae are still billions of times emptier than the air in your lungs. And yet, given enough time and enough gravity, even this whisper-thin material will collapse, condense, and blaze into a star. The interstellar medium is patient in a way that human minds struggle to comprehend, and its patience always pays off. They lurk in the darkness between stars. They don't glow, they don't shine, they don't announce themselves. Molecular clouds are the great hidden giants of our galaxy, cold, dark, impossibly vast regions of dense gas and dust where the universe quietly, slowly, patiently begins building stars. A molecular cloud can span hundreds of light years. The largest, called giant molecular clouds, contain enough material to birth millions of stars the size of our sun. They are, quite simply, the biggest coherent structures within individual galaxies. And yet they're essentially invisible to the naked eye, hiding behind their own thick curtains of dust that absorb starlight before it can reach us. What makes them molecular is that within their cold, sheltered interiors, hydrogen exists not as individual atoms, but as hydrogen molecules, two atoms bonded together into H2. This happens because the density of these clouds is high enough and the temperature low enough for chemistry to occur. These clouds are the universe's cold storage rooms, preserving material in molecular form until gravity decides it's time to wake everything up. Inside molecular clouds are smaller structures, clumps and cores, where density is even higher. These are the true seeds of stars. When conditions are right, when the balance tips between outward pressure and inward gravity, these cores begin to collapse. It starts slowly, imperceptibly, but once begun, it cannot be stopped. There's something deeply moving about molecular clouds. They represent potential, pure, unformed, waiting. Every star you've ever seen in the night sky was once nothing more than a cold, dark clump inside a molecular cloud. Every sun that warms a planet, every light that has ever brightened the dark, it all began here in the silence. Stars don't just appear. They don't emerge from some grand, uniform cloud of gas all at once. The process is far more intimate, far more personal than that. Deep inside molecular clouds, within the cold, dark folds of interstellar matter, are smaller structures, clumps and cores. And these are the actual birthplaces of individual stars. This is where it gets real. A clump is a region within a molecular cloud where the density of gas and dust is noticeably higher than the surrounding material. These clumps can still be enormous, perhaps a few light years across, and they typically contain enough mass to form a small cluster of stars rather than just one. They are the neighborhoods of star formation. Within each clump are even denser regions called dense cores. These are the individual womb-like pockets where single stars or small groups of stars will form. A dense core might be only a fraction of a light year across, tiny by cosmic standards, but it contains the exact conditions needed to kick off gravitational collapse. What makes a core go from stable to collapsing? It comes down to a balance of forces. Gas pressure inside the core pushes outward. Gravity pulls everything inward. As long as these forces are balanced, the core just floats there, cold and still. But if something disturbs that balance, if the core gets too dense, if a nearby supernova sends a shockwave crashing through, gravity wins. And once gravity wins, there's no going back. The collapse is initially invisible. It takes thousands to hundreds of thousands of years, but bit by bit, atom by atom, molecule by molecule, that dark little core is pulling itself together into something extraordinary. It doesn't know it yet, but it will. Of all the forces in the universe, gravity is the most seductive. It doesn't shout, it doesn't flash, it doesn't explode or crackle or radiate heat. It simply pulls, gently, persistently, relentlessly, and it never, ever stops. Every star you see in the night sky owes its existence to gravity. Every planet, every moon, every galaxy. Gravity is not just a force, it is the universe's fundamental creative act. In the context of star formation, gravity plays the role of sculptor. It takes diffuse, spread-out clouds of gas and dust, material scattered across light years of space, and slowly, patiently draws it together into concentrated knots that eventually ignite with nuclear fire. The process is astonishing, from the gentlest, most imperceptible tug to the roaring furnace of a star. The trigger for gravitational collapse can come from many directions. Sometimes it's simply a matter of a cloud becoming massive enough that its own weight overcomes the thermal pressure of the gas inside it. This critical threshold is called the Jeans mass, after the British physicist James Jeans, who first calculated it in the early 20th century. When a cloud exceeds this mass, collapse is inevitable. But gravity rarely works alone. Shock waves from nearby supernova explosions can compress regions of a molecular cloud, pushing them past the tipping point. The spiral arms of galaxies sweep through molecular clouds and trigger bursts of star formation. Even the collision of two galaxies can send gravity-driven ripples through their gas clouds, sparking what astronomers call starburst events, periods of furious, galaxy-wide starbirth. The beautiful irony of gravity is that the very stars it creates will one day die and explode, sending shock waves that trigger yet more star formation. Gravity creates, and then, through stellar evolution, it helps create again. It is the universe's most patient architect, and its work is never done. Every system has a tipping point, that moment when the balance shifts and there's simply no going back. In star formation, that tipping point has a name, the gene's mass, and understanding it is like being handed the secret equation of cosmic creation. In the early 20th century, British physicist James Jeans was grappling with a problem that had puzzled astronomers for decades. What determines whether a cloud of gas will collapse under its own gravity or simply disperse and drift apart? The answer came down to a competition. On one side, gravity, always pulling inward. On the other side, thermal pressure, the tendency of gas to expand and push outward. These two forces are constantly arm wrestling inside every molecular cloud in the universe. When a cloud is small or warm, thermal pressure wins. The gas pushes outward faster than gravity can pull it in, and the cloud puffs up and disperses. But as a cloud grows larger or cools down, gravity gradually gains the upper hand. At some critical mass, the gene's mass, gravity finally overcomes thermal pressure entirely, and collapse becomes inevitable. The gene's mass is not a fixed number. It depends on the temperature and density of the cloud. Cooler clouds collapse at lower masses, which is why molecular clouds, being cold, often just 10 to 30 degrees above absolute zero, are such productive stellar nurseries. The cold slows the atoms down, weakens the thermal pressure, and allows gravity to win at masses that would be insufficient in warmer gas. Once a cloud exceeds its gene's mass, the collapse begins. And as it collapses, it gets denser. And as it gets denser, it gets warmer. And as it warms, the gene's mass changes. The cloud fragments, each fragment collapsing on its own. This is how a single molecular cloud can give birth to dozens or even hundreds of stars. Not one at a time, but in a great cascading rush of creation. Here's one of the most counterintuitive facts about star formation. A single cloud doesn't make a single star. It never works that cleanly. Instead, as a molecular cloud collapses under its own gravity, it breaks apart, fragments into smaller and smaller pieces, each piece collapsing on its own, each destined to become a star. The birth of stars is not a solo performance, it's a symphony. When the initial collapse begins, it doesn't happen uniformly throughout the cloud. Regions that are slightly denser than average collapse faster because their gravity is slightly stronger. As they collapse, they pull in surrounding material, growing denser still. Meanwhile, the overall cloud is also contracting. The result is a hierarchical fragmentation. The cloud breaks into clumps, the clumps break into cores, the cores each form a star. This is why stars are almost never found truly alone. They almost always come in pairs, groups, or clusters. The Pleiades, that beautiful cluster of stars visible on a clear night, were born from a single molecular cloud roughly 100 million years ago. The Orion Nebula's trapezium cluster, those four bright stars at the nebula's heart, were born together from the same collapsing cloud. Birth in the cosmos is nearly always communal. The fragmentation process is governed by a beautiful interplay of forces. Gravity drives the collapse. Thermal pressure resists it. Turbulence within the cloud creates density variations that seed the fragmentation. Magnetic fields thread through the cloud, slowing the collapse in some directions while allowing it to proceed in others. It's a complex, swirling dance, and the outcome, dozens of newborn stars blazing inside what was recently cold, dark emptiness, never loses its power to astonish. The universe doesn't do anything alone, not even create a star. Long before a star shines, before it blazes and burns and illuminates the darkness, it exists in a quieter form. Wrapped in its dusty cocoon, still pulling in surrounding gas, not yet hot enough for nuclear fusion, this is the protostar, the first breath, the beginning before the beginning, and it is one of the most wondrous stages in the entire story of stellar evolution. When a dense core in a molecular cloud begins to collapse, the infalling material doesn't fall smoothly to the center. As it compresses, it heats up. The gravitational energy of the falling gas converts to thermal energy, the same principle that makes a bicycle pump warm when you use it. At first, the cloud is thin enough that this heat radiates away, but as the core becomes denser and more opaque, the heat is trapped, the temperature climbs, and a protostar is born. A protostar is not yet fusing hydrogen. It's a hot, dense ball of gas, opaque, luminous, and still hungry, still pulling in surrounding material through accretion. It radiates energy from its gravitational contraction alone, glowing in infrared wavelengths that human eyes cannot see, but that telescopes like the James Webb Telescope can detect with breathtaking clarity. Around the protostar, the infalling material doesn't all go directly to the center. Rotation causes it to spread into a flattened disk, a protoplanetary disk. This is where planets will eventually form. And perpendicular to the disk, along the rotation axis, powerful jets of material shoot outward at hundreds of kilometers per second, the universe announcing that something extraordinary is happening inside this dusty cocoon. The protostar stage can last hundreds of thousands to millions of years, and when the core finally becomes hot enough, about 10 million degrees, nuclear fusion ignites. The star wakes up. If protostars are cosmic infants, then T-Tauri stars are teenagers, volatile, luminous, full of energy, and not quite finished becoming what they're going to be. They're named after the star T-Tauri in the constellation Taurus, where this class of young stellar objects was first identified in the 1940s. And like teenagers everywhere, they are fascinating, unpredictable, and fundamentally in transition. T-Tauri stars are young, sun-like stars in the final stages of their formation. They're still accreting material from their surrounding disks, but nuclear fusion has not yet fully stabilized in their cores. They are variable, their brightness fluctuates irregularly because their surfaces are covered in enormous star spots and because material accreting from the surrounding disk falls onto the star in uneven streams, causing dramatic flares and brightness changes. These stars shine far more brightly than their fully formed counterparts would suggest, not from nuclear fusion alone, but from gravitational contraction. They're still shrinking, still compressing, still converting gravitational energy into heat and light. Their surfaces can be covered with activity, stellar flares, enormous magnetic fields, powerful solar winds that would make our own sun look placid by comparison. One of the most significant things about T-Tauri stars is their relationship with their surrounding disks. Strong stellar winds and radiation from the star slowly erode and disperse the disk material. Some of that material accretes onto the star, some is blown away into space, and some, crucially, sticks together to form planetesimals, the building blocks of planets. The window for planet formation is narrow, perhaps only a few million years, and T-Tauri stars are right at the center of it. Watch a T-Tauri star long enough and you'll see a solar system being assembled from scratch. The material is messy, the process is violent, but the outcome, eventually, can be a world. There's a reason planets orbit the sun in roughly the same plane, all spinning in the same direction. There's a reason our solar system is flat like a disk rather than spherical like a ball. The answer traces back to a fundamental fact about physics. Angular momentum is conserved. And this single rule, playing out over millions of years, gives the universe one of its most elegant and recurring structures, the accretion disk. When a molecular cloud core collapses to form a protostar, not all the material falls directly inward. The cloud was rotating, however slightly. As it collapses and gets smaller, like a spinning ice skater pulling in their arms, it spins faster. Conservation of angular momentum means that material can't simply fall straight in. It overshoots, circles around, and settles into a rotating disk around the young star. And in that disk, the story of planets begins. Accretion disks around young stars are not calm, orderly places. They're turbulent, churning regions of hot gas and dust, laced with magnetic fields that drive instabilities and create eddies and vortices. Material spirals inward slowly, and as it does, it heats up, glowing in infrared and sometimes even visible light. The inner edge of the disk closest to the star can be thousands of degrees, hot enough to vaporize rock. Farther out in the disk, beyond what astronomers call the snow line, temperatures drop low enough for water ice to form. This is where rocky and icy material clumps together more easily, building larger and larger bodies. First pebbles, then boulders, then planetesimals, then planetary embryos, and finally planets. In our own solar system, the snow line sits roughly between the orbits of Mars and Jupiter, which is why the rocky planets are inside it and the gas giants beyond. The accretion disk is the cradle of worlds, and it all begins with a spinning cloud. You can't see them, you can't feel them, and yet magnetic fields are one of the most powerful and pervasive forces shaping the birth of every star in the universe. They are the hidden hand threading through every molecular cloud, every collapsing core, every spiraling protostellar disk, subtly steering the whole process in ways that astronomers are still working to fully understand. Molecular clouds are threaded with magnetic field lines that run through the gas like invisible wires. These field lines resist being compressed. If you try to push gas perpendicular to magnetic field lines, the field pushes back. This means that when a molecular cloud begins to collapse, it's not a perfectly symmetric implosion, it's an asymmetric one. Gas can flow more easily along magnetic field lines than across them, so collapse tends to happen preferentially in one direction. This is why some molecular cloud cores end up flattened rather than spherical. The magnetic field literally sculpts the shape of the collapsing structure. Magnetic fields also play a role in slowing down star formation. Without magnetic resistance, molecular clouds might collapse and form stars far faster than they actually do. The fact that it takes millions of years for a molecular cloud to convert its gas into stars is partly due to magnetic braking, the way field lines connect the collapsing core to the surrounding cloud and transfer angular momentum outward, slowing the collapse. In protostars, magnetic fields drive the spectacular jets, those collimated streams of material that shoot out along the rotation axis at enormous speeds. These jets are one of the clearest signs that a protostar is alive and active deep inside its dusty shroud. And they too are shaped and launched by the interaction between the spinning disk and the star's magnetic field. The universe is not just held together by gravity, it is also, quietly, sewn together by magnetism. Chaos and creation are not opposites. In the universe, they are partners. And nowhere is this more evident than in the turbulent interior of a molecular cloud, where the swirling, churning, chaotic motion of gas plays a fundamental role in determining where stars form, how massive they become, and how quickly they ignite. Turbulence is not an obstacle to star formation, it is one of its engines. Molecular clouds are not calm places. Despite their cold temperatures and vast, slow timescales, they are internally turbulent, stirred by the motions of their own gas, by the energy input of young stars forming within them, by the passage of spiral arm density waves, by the shock waves of supernovae nearby. Radio observations of molecular clouds show gas moving at supersonic speeds in complex, tangled patterns. This turbulence creates density fluctuations throughout the cloud. And those fluctuations matter enormously. In the regions where turbulence happens to compress the gas slightly, density rises, and higher density means stronger local gravity. So turbulence seeds the formation of dense cores, the very structures that collapse to form protostars. In this way, the chaos of turbulence plants the seeds of the most orderly things in the universe, stars. But turbulence is a double-edged force. The same turbulence that seeds star formation also resists it. The turbulent pressure, the kinetic energy of randomly moving gas, contributes to the outward pressure that fights against gravitational collapse. This is one reason why star formation is inefficient. Only a few % of a molecular cloud's mass actually ends up in stars. The rest is dispersed by turbulence, stellar winds, and radiation. This inefficiency is paradoxically a gift. If stars formed too efficiently from molecular clouds, galaxies would have burned through all their gas in the first billion years. The chaotic turbulence that seems to impede star formation is the mechanism that lets star formation continue across cosmic time, right up to the present day. The moment a star truly switches on, something remarkable happens to its neighborhood. High-energy radiation, ultraviolet light, X-rays, streams outward from the newborn stellar surface and crashes into the surrounding gas with enough energy to strip electrons from hydrogen atoms. This process, called ionization, transforms the cold, dark molecular cloud into something blazing and brilliant. This is how a nebula is born, not just as a cloud of gas, but as a glowing beacon of light. Ionized hydrogen, a proton stripped of its electron, is the primary ingredient of emission nebulae, the classic glowing cosmic nurseries. When the stripped electron eventually recombines with a proton, it releases energy in the form of photons. The characteristic red glow of emission nebulae comes from hydrogen recombination, specifically from the transition called H-alpha, where electrons drop to the second energy level and emit red light. It's the universe's most iconic color, and it announces the presence of a young, hot star somewhere inside. The region of ionized gas around a young star is called an H2 region. These regions can be enormous, sometimes spanning hundreds of light years, and they glow with the combined light of thousands of young stars working together to keep the surrounding gas hot and luminous. The Orion Nebula is an H2 region, so is the Eagle Nebula, the Lagoon Nebula, and the Tarantula Nebula. As young stars ionize the surrounding gas, they also heat it dramatically. Gas that was previously just degrees above absolute zero is suddenly heated to 10,000 degrees or more. This massive pressure increase causes the ionized gas to expand outward, creating a bubble that grows over time. Eventually, this expanding bubble of hot ionized gas collides with the surrounding molecular cloud, compressing it and potentially triggering yet another round of star formation in the compressed material. Stars make the conditions for more stars. If you want to find where the universe is making new stars right now, not millions of years ago, but actively, presently, at this very moment, look for emission nebulae. These are the great cosmic factories, the blazing breeding grounds where gas and gravity and light collide to produce the next generation of suns. They are the universe's most productive, most dramatic, most visually stunning manufacturing facilities, and they have been running for billions of years without pause. An emission nebula is a cloud of ionized gas that glows because young, massive stars within it are bombarding it with ultraviolet radiation. The gas absorbs this radiation and re-emits it as visible light, particularly in the red wavelengths of hydrogen emission and the green-blue wavelengths of doubly ionized oxygen. The result is those extraordinary glowing curtains of color that fill our deepest telescope images, pinks and reds and teals swirling together in formations that seem almost too beautiful to be real. But emission nebulae are more than just beautiful, they are violent. The young massive stars at their centers, called O and B-type stars, are some of the hottest, most energetic stars in existence. They pour out radiation at staggering rates. Their stellar winds howl outward at thousands of kilometers per second, carving enormous caverns and bubbles in the surrounding gas. They erode the cloud even as they formed from it, sculpting the pillars, arches, and globules that give famous nebulae their distinctive shapes. This erosion creates a fascinating feedback loop. As the hot stars eat away at the nebula's edges, they compress the material just ahead of the ionization front. This compression can trigger new star formation in the dense rims and pillars, a process called triggered star formation. The old stars, in pushing outward, birth the new. The nebula is never passive. It is always, in some part, consuming itself to create its next chapter. 17. Dark nebula, the shadows that hide new stars. Not all nebula glow. Some of the most significant, most star-rich structures in the galaxy are the ones you can't see at all. Not because there's nothing there, but because there's too much. Dark nebula are dense clouds of interstellar dust so thick that they absorb and scatter almost all visible light passing through them. They are the shadows on the face of the galaxy, and inside them, hidden from our view, some of the most active star formation in the cosmos is underway. Look at any wide-angle photograph of the Milky Way on a clear, dark night, and you'll notice dark patches interrupting the glow. Those aren't gaps where there are no stars. Those are dark nebula blocking the view of the stars behind them. The Great Rift, that dark band running through the Milky Way's center, is actually a collection of overlapping dark nebula strung along our galaxy's disk. The dust in dark nebula is what makes them so opaque. Microscopic grains of silicates, carbon, and ices scatter and absorb visible light with extraordinary efficiency. What gets through is reddened and dimmed almost beyond recognition. But infrared light, longer wavelength radiation that passes through dust far more easily, can pierce these clouds. And when astronomers point infrared telescopes at dark nebula, they find them teeming with protostars, young stellar objects, and all the messy, luminous activity of active star formation. The most photogenic dark nebula are those silhouetted against brighter backdrops. The Horsehead Nebula, perhaps the most recognizable dark nebula in the sky, is a dark pillar of dense gas rising against the glowing emission nebula IC 434 in Orion, the Coal Sack in the Southern Cross, the Snake Nebula. These dark structures are not empty. They are full of potential, full of forming stars, full of the future. They look like holes in space, small, round, almost perfectly dark spots, like cosmic punctuation marks printed against the glowing backdrop of emission nebula. But Bok globules, named after Dutch-American astronomer Bart Bok, who first studied them systematically in the 1940s, are not holes. They are among the most intimate, most self-contained stellar nurseries in the universe. And inside their dark, compact cores, individual stars are being born in remarkable isolation. A Bok globule is a small, dense, cold cloud of gas and dust, typically spanning less than a light-year across and containing anywhere from 1 to several times the mass of the Sun. They are compact enough that their own gravity easily overcomes the thermal pressure of the gas inside, meaning they are almost always collapsing, almost always in the process of forming a star. Over half of all known Bok globules have been found to contain embedded protostars when examined in infrared light. What makes Bok globules special is their simplicity. The star formation happening inside a giant molecular cloud is chaotic, multiple stars forming simultaneously, turbulence, shock waves, stellar feedback complicating everything. A Bok globule is almost surgically clean by comparison. One cloud, 1 or 2 forming stars, a clear, contained system that astronomers can study and model with relative precision. Barnard 68 is perhaps the best-studied Bok globule. It sits about 500 light-years away, appears as a perfectly round, utterly dark spot against the star fields of the galaxy's ear regions, and contains roughly twice the mass of our Sun. It is cold, just 16 degrees above absolute zero, and it is collapsing. In perhaps 200,000 years, a new star will ignite inside it, and Barnard 68 will join the long list of stellar nurseries that have fulfilled their cosmic purpose. These small, dark globules remind us that star formation doesn't always happen with drama and spectacle. Sometimes, in quiet isolation, the universe simply makes a star. Not all beauty is born from fire. Some of the most ethereal, hauntingly lovely objects in the night sky are not generating their own light at all. They're simply reflecting it. Reflection nebulae are clouds of interstellar dust that scatter the light of nearby stars, glowing not with their own power, but with borrowed radiance. They are the universe's most patient mirrors, and what they reflect is often worth the looking. The physics of reflection nebulae is the same physics that makes the sky blue. Dust grains in the nebula scatter light, and they scatter shorter wavelengths, blues and violets, more efficiently than longer ones. This is why reflection nebulae typically appear blue in astronomical photographs, even when the stars illuminating them are white or yellowish. The Pleiades star cluster is surrounded by a beautiful reflection nebula, a faint blue-gray veil of scattered starlight that gives the cluster its softly hazed appearance in long-exposure photographs. Unlike emission nebulae, reflection nebulae are not hot enough to be ionized. The stars illuminating them lack sufficient ultraviolet radiation to strip electrons from hydrogen atoms.
Instead, the dust simply scatters whatever light falls upon it. The result is a softer, more diffuse glow than the vivid colors of emission nebulae, more like candlelight than bonfire. Reflection nebulae often exist alongside emission nebulae in star-forming regions. The same complex of gas and dust that contains hot young stars blazing in H-alpha red might also contain cooler, less luminous stars surrounded by blue reflection halos. Regions like the Orion molecular cloud contain both types, creating compositions of contrasting color and texture that look almost like paintings, and have, in fact, inspired generations of artists and astronomers alike. They are reminders that even borrowed light can be beautiful, that you don't have to generate your own glow to be worth watching. There are images that change how you see the universe. The 1995 Hubble Space Telescope photograph of the Eagle Nebula's Pillars of Creation is undeniably one of them. Towering columns of gas and dust, each one longer than our entire solar system is wide, sculpted by stellar winds and radiation into shapes that look almost geological, almost like something from a landscape rather than outer space. It is one of the most reproduced scientific images in history, and it tells a story of creation and destruction simultaneously. The pillars are located inside the Eagle Nebula, about 6,500 light-years away in the constellation Serpens. They are dense columns of hydrogen gas and dust being eroded by the intense ultraviolet radiation of massive young stars in the nearby star cluster NGC 6611. This erosion is a process called photoevaporation. The radiation heats the surface of the pillars so intensely that the gas boils away into space, carrying dust with it. The pillars are literally being eaten alive by starlight. But here's the profound paradox. Even as the pillars erode from the outside, they are forming stars on the inside. Along the edges and within the dense cores of each pillar, new protostars are condensing from the compressed gas. The same radiation that destroys the pillar's surfaces also compresses their interiors, potentially triggering star formation that wouldn't have occurred otherwise. Destruction and creation happening simultaneously in the same structure, driven by the same force. At the fingertip-like protrusions at the tips of each pillar are EGGs, evaporating gaseous globules, dense knots of material being exposed by the surrounding photoevaporation. Some of these EGGs contain protostars. Others are just dense gas blobs that will evaporate before they ever form a star. The pillars of creation are not eternal. They may already have been destroyed by a supernova, but because the Eagle Nebula is so far away, that light hasn't reached us yet. The stars forming inside them, though, will survive. Creation outlasts its own nursery. You don't need a telescope to find it. On a clear winter night, look at the constellation Orion, the Hunter. Find the 3 stars of his belt, then look just below them for his sword. The middle of those 3 points is not actually a star, it's a nebula. It's the Orion Nebula, and at roughly 1,300 light-years away, it is the nearest large star-forming region to Earth, our cosmic neighbor, our nearest nursery. The Orion Nebula, cataloged as M42, spans about 40 light-years across and contains enough gas and dust to form thousands of stars. At its heart blazes the Trapezium cluster, 4 massive young stars whose ultraviolet radiation ionizes the surrounding gas, causing it to glow in that distinctive pinkish-red hue. These stars are only a few 100,000 years old, practically newborns by cosmic standards, and they're already reshaping everything around them. What makes the Orion Nebula so scientifically valuable is not just its proximity, but its richness.
Deep inside its clouds, astronomers have identified over 700 young stellar objects, stars in various stages of formation, from protostars still embedded in their dusty cocoons, to T-Tauri stars in their turbulent adolescent phase, to fully formed but very young stars already clearing the gas from their immediate surroundings. Hubble's Space Telescope observations of the Orion Nebula have revealed something extraordinary. Around many of its young stars orbit protoplanetary disks, flattened disks of gas and dust in which planets are actively forming. These disks, silhouetted against the nebula's bright background as dark ovals, are called proplids. Over 150 proplids have been identified in Orion alone. We are literally watching solar systems being assembled. Every clear winter night, that faint smudge in Orion's sword is doing something that took our own solar system millions of years. It's making worlds, right now. Most cosmic nurseries are impressive. The Tarantula Nebula is in an entirely different category. Located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 160,000 light-years away, the Tarantula Nebula is the most intensely star-forming region in our entire cosmic neighborhood. Nothing else comes close. If it were as close to Earth as the Orion Nebula, it would be bright enough to cast shadows at night. The Tarantula Nebula, also called 30 Doradus, spans about 1,000 light-years. Its mass dwarfs the Orion Nebula by orders of magnitude. At its center is the star cluster R136, which contains some of the most massive and luminous stars known to science. Stars with masses exceeding 100 times the mass of our Sun, blazing with over 1,000,000 times the Sun's luminosity. These are stellar monsters, and they are young, only a few million years old, burning through their fuel at rates that mean they will last only a few million more years before exploding as supernovae. The Tarantula Nebula is classified as a starburst region, a place where the rate of star formation is far higher than in typical star-forming regions. The conditions here are extreme. Higher densities, stronger radiation fields, more turbulence, more shock waves from supernova explosions. The feedback between star formation and stellar death is amplified and accelerated. Stars form, explode, compress the surrounding gas, trigger more star formation, a chain reaction running for tens of millions of years. This region is also our closest example of conditions similar to those in the early universe, when galaxies were actively assembling and star formation rates were far higher than today. Studying the Tarantula Nebula is, in a sense, a form of time travel, a glimpse into the universe as it was billions of years ago, when cosmic nurseries like this were common and the galaxy was young. A star is not a passive object. From the moment of its birth, it pushes back against the universe. It radiates heat and light outward in all directions. It drives a constant stream of charged particles, its stellar wind flowing outward at hundreds to thousands of kilometers per second. And for a young, massive star, this wind is powerful enough to reshape, hollow out, and eventually destroy the very cloud from which it was born. Stars are violent midwives of their own creation. Stellar winds from young, hot, massive O and B-type stars are some of the most powerful in the universe. These stars shine so brightly that the pressure of their own radiation accelerates material off their surfaces, launching a constant outflow that can strip mass at rates millions of times greater than the sun's own solar wind. When this wind crashes into the surrounding gas of a nebula, it creates a bubble. Literally a spherical cavity in the cloud, filled with superheated plasma and expanding at high speed. These stellar wind bubbles are a fundamental part of the ecology of star-forming regions. They compress gas at their edges, potentially triggering new star formation in the swept-up shells. They inject energy into the turbulent mix of the molecular cloud, stirring and heating and disrupting. They carve out the spectacular cavities and sculpted edges visible in the most famous nebula images. Seen from a distance, the combination of stellar winds and radiation from a cluster of young stars creates an H2 region bubble, a glowing cavity of ionized gas rimmed by compressed molecular material, with the stars blazing at the center. The Rosette Nebula is a beautiful example, a ring-shaped emission nebula surrounding an open star cluster, the central cavity carved entirely by stellar winds. The nursery always outlives the stars that clear it, but those stars were only possible because of the nursery. The relationship between stars and their birth clouds is one of the universe's most violent and beautiful partnerships. The universe has an extraordinary capacity for recycling. Nothing is ever truly wasted. When a massive star reaches the end of its life and detonates in a supernova, the explosion doesn't just destroy, it creates. The shock wave from that supernova travels outward through the surrounding interstellar medium, and when it hits a molecular cloud, it compresses the gas at the cloud's edge. That compression can push portions of the cloud past their Jeans mass, triggering a new round of star formation. Old stars, in dying, give birth to new ones. This process is called triggered star formation, and it operates at multiple scales throughout the galaxy. Supernova shock waves are one trigger. The expanding bubbles of ionized gas around young H2 regions are another. As the bubble expands, it sweeps up surrounding gas into a dense, compressed shell, and stars can form in that shell in a process called collect and collapse. Even the spiral arms of galaxies act as triggers, compressing gas as they slowly rotate through the disk. The sequential nature of triggered star formation means that star-forming regions are often self-perpetuating. One generation of stars forms, evolves, and eventually drives the formation of the next generation nearby. This process, called sequential star formation, can propagate across a molecular cloud complex over tens of millions of years, with successive waves of starbirth moving outward like ripples from a stone dropped in water. There's something philosophically profound about this process. The sun, our sun, may itself have been triggered into existence by a nearby supernova some 4.6 billion years ago. Evidence for this includes an excess of certain isotopes in primitive meteorites that could only have been produced by a massive star that exploded shortly before our solar system formed. We may owe our very existence to a star that died in order to make room for us. Creation is never truly spontaneous. It is always downstream of something else. If you want to understand the universe, understand this one thing. Nothing is ever truly created from nothing, and nothing is ever truly destroyed. Matter cycles. Energy cycles. The atoms in your left hand may have spent billions of years inside a massive star before being scattered by a supernova, drifting through interstellar space, cooling into a molecular cloud, collapsing into a new star, being ejected again, and eventually finding their way into you. The universe is not a story of creation and destruction, it's a story of transformation. Stars are the universe's primary transformation engines. They take the simplest material, hydrogen mostly, and through nuclear fusion convert it into heavier elements: helium, carbon, oxygen, silicon, iron. This nucleosynthesis is the origin of nearly every element heavier than hydrogen and helium in the periodic table. Every atom of calcium in your bones, every atom of iron in your blood, every atom of oxygen in the water you drink, all of it was forged in a stellar interior. When a star dies, how it dies depends on its mass. A star like our sun will eventually swell into a red giant, shed its outer layers as a beautiful planetary nebula, and leave behind a dense white dwarf, a slowly cooling ember that will glow for billions of years. A more massive star meets a far more dramatic end. Its core collapses in milliseconds, triggering a supernova explosion that, for a brief moment, outshines entire galaxies. The explosion scatters the star's processed material, all those heavy elements forged over millions of years, back into the interstellar medium. And there, in that scattered debris, the cycle begins again. The material enriches the surrounding molecular clouds. New stars form from this enriched material. Those new stars are chemically more complex than the ones before them, capable of hosting planets, capable of hosting chemistry sophisticated enough, eventually, to produce life. The universe is not just cycling matter. It is, through each cycle, becoming more complex, more interesting, more alive. There is perhaps no more dramatic sight in all of astronomy than a supernova remnant. These expanding shells of superheated gas, glowing in twisted filaments of shockwave-heated plasma, stretching across tens of light-years of space, they are the aftermath of the most violent events in the universe. They are the wreckage, the rubble, the scarred landscape left behind when a massive star detonates. And they are, paradoxically, among the most productive star-forming structures in the galaxy. When a massive star exhausts its nuclear fuel, its iron core collapses in a fraction of a second. The collapse releases more energy than the sun will emit over its entire 10 billion-year lifetime, and it releases it in milliseconds. This energy drives a shockwave outward through the star's outer layers, ejecting them at velocities of tens of thousands of kilometers per second. The explosion is a supernova, and the expanding shell of ejected material is its remnant. As the remnant expands into the surrounding interstellar medium, it sweeps up gas and dust like a cosmic snowplow. The shockwave heats this swept-up material to millions of degrees, causing it to radiate in X-rays. Behind the shockwave, where the gas has cooled slightly, it glows in visible light, those twisting, tangled filaments that make supernova remnants so visually spectacular. The Crab Nebula, remnant of a supernova observed by Chinese astronomers on July 4, 1054 AD, is still expanding today, nearly 1,000 years later. At its center pulses a neutron star, the ultra-dense remnant of the collapsed stellar core, spinning 30 times per second and lighting up the surrounding nebula with its high-energy radiation. But the supernova remnant's most important role is invisible, the way its shockwave compresses surrounding molecular cloud material, triggering the formation of new stars and new solar systems. Death in the cosmos is never the last word. Somewhere in the Orion Nebula right now, around a star not so different from the young sun, a disk of gas and dust is orbiting. Slowly, patiently, the material in that disk is clumping together. Dust grains are sticking to one another. Pebbles are building into boulders. Boulders are building into planetesimals. And planetesimals are beginning the long process of building a planet. We are watching, in real time, the birth of another world. And the name for the structure making it happen is a protoplanetary disk. Protoplanetary disks form naturally as a consequence of angular momentum conservation during the collapse of a molecular cloud core. As the collapsing material spins faster and faster, it flattens into a disk around the young protostar. This disk inherits the rotation of the original cloud, and within it, the chemistry and physics of planet formation play out over millions of years. In the inner disk, where temperatures are high, rocky materials, silicates, metals, dominate. Here, terrestrial planets like Earth and Mars can form. In the outer disk, beyond the snow line, ices of water, methane, and ammonia provide additional material for solid bodies, and the higher density of solids allows planetary embryos to grow large enough to gravitationally capture the surrounding hydrogen and helium gas, forming gas giants like Jupiter and Saturn. Hubble and now the James Webb Space Telescope have imaged protoplanetary disks in extraordinary detail. The images reveal gaps and rings in the dust, carved by forming planets whose gravity has swept their orbital paths clear. These gaps are direct evidence of planets forming in real time. We are no longer speculating about how our own solar system formed. We are watching it happen in other systems right now. Every planet in the universe, rocky, gassy, icy, began as a thin smear of dust in a protoplanetary disk. Every moon, every asteroid, every comet. It all starts with a spinning disk around a young star and patience measured in millions of years. Here is something remarkable about the night sky. Most of the points of light you see are not single stars. They are paths. Systems of 2, 3, 4, or more stars orbiting one another in intricate gravitational dances that can last for billions of years. Our own sun, traveling alone through the galaxy with its family of planets, is something of an oddball. The universe strongly prefers its stars to come in company. Binary and multiple star systems form from the same fragmentation process that makes star clusters. When a molecular cloud core collapses and fragments, the resulting pieces don't always fly apart. If 2 or more fragments form close enough together that their mutual gravity binds them, they will orbit one another as a binary or multiple system. The separation between the stars can range from less than the distance from the Earth to the Moon to hundreds of times the distance from the Earth to the Sun. The variety within binary star systems is extraordinary. Some binaries are so close that the stars are practically touching. Contact binaries, where the two stellar surfaces actually share a common envelope of gas. Some are so wide that they orbit each other once every millions of years, their separation so vast that they can barely be recognized as gravitationally connected. And some binary systems are dynamically unstable over long timescales, with one star eventually being ejected while the other settles into a slightly different orbit, a gravitational divorce played out over millions of years. Binary systems have been crucial to our understanding of stellar physics. Because we can measure the orbital dynamics of binaries precisely, we can calculate the masses of both stars with extraordinary accuracy, something impossible for isolated stars. They are, in essence, the universe's most reliable scales. And they remind us of something important. Even the stars, born from the same cloud of darkness, prefer not to be alone. Our galaxy is alive. Not metaphorically, literally, actively, presently alive with the ongoing process of starbirth. The Milky Way is not a museum of old stars quietly burning out in the dark. It is a dynamic, evolving system that is still manufacturing new suns, still adding new solar systems, still building its future one star at a time. Right now, while you read this, new stars are igniting in molecular clouds not terribly far from where we sit in the galaxy's outer disk. The Milky Way produces roughly 3 to 4 new stars per year on average. This rate is modest compared to the frenzied star formation of the galaxy's distant past. When the Milky Way was young, it likely formed hundreds of stars per year. But the process is far from over. Distributed across the galaxy's disk are thousands of molecular clouds, giant repositories of gas and dust that will eventually give birth to new generations of stars. The nearest active star-forming regions to our solar system include the Orion Molecular Cloud Complex, the Taurus-Auriga Complex, and the Ophiuchus Cloud, all within about 500 light-years. These are our cosmic neighbors, busy at work making the next generation of stars. Some of those stars may be forming planets right now. Some of those planets may become worlds not entirely unlike our own. The star-forming regions of the Milky Way are concentrated primarily in the galaxy's spiral arms, those sweeping, luminous structures that give spiral galaxies their characteristic shape. The spiral arms act as density waves, slowly rotating through the disk and compressing gas as they go, triggering bursts of star formation in their wake. The bright blue-white stars that define the arms are there precisely because they are so young, born from the arm's compressive trigger, that they haven't had time to drift away yet. Our galaxy is not finished. It is still writing its own story, one star at a time. We began this journey with a cloud, cold, dark, impossibly vast, a molecular cloud drifting through the galaxy, waiting for gravity to call it to order. We watched it collapse, fragment, and ignite. We saw protostars wrapped in their dusty cocoons, protoplanetary disks assembling worlds, stellar winds carving the brilliant nebulae that make the universe look like a masterwork of art. And now we arrive at the end of the story, except it's not the end at all. It's where the story becomes personal. Every atom in your body was made in a star. Not metaphorically, not poetically, literally, physically, provably. The carbon in your DNA, the calcium in your bones, the iron in your blood, the oxygen in every breath you take. These atoms did not exist when the universe began. They were forged over billions of years inside stellar interiors, scattered by stellar explosions, gathered into new molecular clouds, collapsed into new stars, and eventually, through a chain of cosmic events too long and intricate to fully trace, found their way into the planet Earth, into the biosphere, and into you. The nebulae we've been exploring are not distant, exotic curiosities. They are our family history. The Orion Nebula, the Eagle Nebula, the Tarantula, these are the kinds of places where the atoms that make up your body were born. They are the beginning of a chain of events that leads, billions of years later, to a human being standing on a rocky planet, looking up at the night sky and wondering where it all came from. The astronomer Carl Sagan said it best, "We are a way for the cosmos to know itself. We are made of star stuff, of the same hydrogen that fills molecular clouds, of the same heavier elements that stellar fusion and supernova explosions have been building for 13 billion years. The universe, in creating us, has created something capable of looking back at it and recognizing itself." The birth of nebulae is not just the birth of stars, it is ultimately the birth of everything, including you. Look up at the night sky, find that faint smudge in Orion's sword, and know that cloud made you possible. That darkness is where light and life begins.